I will be going through SVD in the easiest way I know how. So we'll start with our matrix here. 1, 1, 0, 2, 2, 0. Alright. So we should just notice that this is a tall matrix. And what we're going to be working towards is reconstructing the matrix with this formula. So pretty much what we first want to recognize is that if this is not a square matrix. So we need to multiply it by its transposition, or transpose it first and then multiply it by the original. And each of those will correspond to a different thing. So if we were to do this would correspond to the V value. And if we were to do this would correspond to the U. So, but what we should notice right here is that this is a 3x2 matrix. And if we're just gonna transpose it first and multiply, it will become a 2x3 times a 3x2, which will reduce to a 2x2, which will be easier to deal with. So I'm gonna go for this right here. So yes, first I'll transpose. Alright, so that's a transposition. This is the original, and now we're just gonna multiply. So 1. Now we have our matrix. 5, 1, 1, 5. And from this, we need to get the eigenvalues. So since this is a 2x2 matrix, there's a nice little shortcut to get the eigenvalues, which is just the trace midpoint plus or minus square root of trace squared plus 4 times determinant all over 2. That's going to be our eigenvalues. And there's going to be 2 coming from a 2x2 matrix. So this does it properly. Yeah. So if we see the trace midpoint between 5 and 5, we just have 5. And the trace itself would be 10 here. 10 squared. 4 times determinant. So the determinant just going to be for 2x2 matrix, AD minus BC. So that's going to be 25 minus 1, 24, 24. Oh, this is minus. I meant to put minus there. Over 2. So then we have 10 squared minus 4 times 24 all over 2. And we're going to realize, or square root of all of that. And we're going to realize this would just simplify to 1. So then 1 plus or minus 5. And we're going to end up with 2 eigenvalues. So that's going to be 6. And we're going to have 4. So now that we have these, what we can do is we can go, there's 2 things we could do. We could either try to get the singular values from these or get the eigenvectors. So I'll do the eigenvectors first. So now we're going to go back up to our matrix up here. And we just need to solve for the null space, but first we need to subtract the lambdas. Yeah. So first we're going to do this. And then this you'll notice that, well, the rows cancel out. So you'll have a row of zeros, and then you'll end up with something that looks like this for RREF. And I will just, now we just have to write this as the null space form. So I'll notice the first line is that, and second line, there's nothing, but there's like the dependent variable, so you just set that equal to itself. and then you add that both sides, you'll eventually end up with, and then, yeah, that will be 1, 1. One other thing we have to do is we just have to normalize this. And the way we can do that, divide it by its magnitude, which is going to be 1 squared plus 1 squared, square root of all that. So 1 over, or root 2, and another way to write that is just by this, 1 over root 2. Alright. And next thing that we will end up doing is we're just going to solve for the other eigenvector. So, yeah. So this was our original MTM, but now we're just going to subtract by the lambda 2. So, and we'll end up with 1, 1, 1, 1. If you simplify this, you'll notice that our REF is going to be this. And to write in null space, we're going to end up with you'll see negative 1, 1. Alright. And that is useful. But we still got to normalize it, divide by magnitude, which is actually going to be the same as previous, 1 squared over that, okay, over root 2. And now we have our 2 eigenvectors. Yeah. So if we want to stack both our eigenvectors, we will end up with, we can do the previous one and then this one. Oh, I should probably do the over root 2, so that's fine. Yeah. Root 2, root 2, root 2, root 2. So if we go back to that original formula, G equals U sigma VT. This right here is V. Alright. So I'm going to go ahead and we're going to get sigma first. So you'll notice that I'm just going to do a square form for this because we're going to be doing a shortcut trick and it will come to make sense soon. So the singular values for this are just going to be the lambdas, which were 6 and there are 4, and you just do the square root of them. And then it's just from like the identity matrix. So you just put them on the values that correspond to that. So root 6, 2, 0, 0. Yep. And now we're going to see something interesting. So normally if we want to go from V, or if we want to find U, we would just have to solve the eigenvectors separately. But there's a cool little simplification that we can do. And pretty much it just has to do with, we have the original matrix times our V times the inverse of the sigma will actually just give us directly our U. So what I'm going to go ahead is we're going to take this thing right here that we calculated, or actually the original matrix, multiply with this, and we're going to multiply with the inverse of this, and we're going to end up with directly our U, and then we can reconstruct the whole matrix from there. Alright. Alright, so now we have this matrix, and we're going to go ahead and multiply it by the inverse of sigma, which is right here. So the inverse of this, if you were to do the simplification through the Gaussian elimination method, you'd realize that it just comes to 1 over root 6. Yep, 0, 0, 1 over 2. Since there's only the diagonal columns, like you try to shift rows, like there's nothing really to shift. So now I'm just going to do that multiplication. Alright, so now we end up with this matrix. And I can definitely make this cleaner because we have roots in the denominator, but that's not all that important right now. Or I will when we do the full multiplication. But now we're going to refer back to that original formula. So this right here is actually u, okay? And we had v. V was our first one. So that was just 1 over root 2, 1 over root 2, 1 over root 2 negative. Or yeah, it's that one that's negative. So yeah, this is negative. And our sigma is this. As we remember this. Alright. So now when we combine all of these together properly, I mean we'll have to transpose this, it will be able to reconstruct the original matrix. Our V transposed, which will just be over here. Alright, so this is our reconstruction, but now I'm going to simplify the roots, and you'll see that's the same thing. So the square root of 144 is actually 12. 1 over 6, 1 over 6, 0, 2 over 6. 2 over 6, and 0. Alright, and now we'll realize that if we just multiply it up with 1, 1, 0, 2, 2, 0. And if we flip back, we'll realize that is our original matrix and our job has been done.